Welcome to breadboarding. In this video, what we're going to be doing is taking the original binary dump of the ROM from the 1981 ROM, which we've been using in the project so far, and we're going to disassemble it into assembly language source, and then we're going to recompile it again or reassemble it back into binary form, and we'll compare the binary before and after. We should be able to get exactly the same binary content if we've got the source code properly. Now, it might seem a bit strange to want to do this, but what this allows us to do is to establish that the source that we've got does rebuild the original binary, and then that will allow us to enhance and make changes to the existing Monitor ROM. So, for example, we'll be able to change the save and load routines, perhaps to use a serial port in future episodes. And I wanted to also look at the reason why we had a bit of ghosting on some of the LED displays when we look at it on the camera. So this is really going to show you how to take a binary dump of a ROM or any program really and disassemble it and make sense of the way how it's all organized. So in order to do this, we're going to be using our original 2 kilobyte ROM, which we've got stored in a file. If you remember from video 5, we saved this using an EPROM programmer. So Nanocomp 6809.1981.bin is our original image of the ROM. And we know that the example programs are in the first 1 kilobyte, which is normally configured to be 7800 up to just below 7C00, so that's 7BFF. And the monitor itself is located at 7C00 up to the top of the ROM. That's the 7FFFE. And remember that in the Nanocomp design, it only makes use of the bottom 32K of address space. It doesn't use the top A15 line, which is the reason why we're not talking about the FFFE, which the datasheet will talk about. We know from earlier videos that the reset vector is located at the top of the memory at the 7FFE to 7FFF. And that the reset code is currently 7D89. So this gives us an entry point that we know that the byte starting at 7D89 should be executable, and we can also then work out from other information we know what other executable bits of code there are in the ROM. One of the issues are there are blocks of data and null zero padding in some parts of the ROM, and we'll see when we disassemble it that if we don't mark these out as data rather than being executable code, that we won't get sensible information through. Now, there's lots of different disassemblers and assemblers out there for 6809. I'm not saying that the ones I'm using are better than any others, but they just happen to work for what I wanted. In this particular case, the 6809 DASM Disassembler is at this address. And if we just click on this, I'll show you where that comes from. So there is a link here for the 6809 DASM modified version, and this was modified a little bit after the original version, and we're just going to download that, and that's just a zip file about 50k, and we'll look at recompiling that. Now, I've compiled this under Linux. I do have Windows subsystems for Linux using Ubuntu on my Windows machine. I'm not going to cover how to install that, but it's fairly straightforward if you Google for it to install Windows subsystem for Linux using Ubuntu. I just found that since this disassembler seems to work well under Linux, I haven't tried to get it working under Windows. And since it's only going to be used a couple of times, I didn't really try very hard to see if I could make it run under Windows. So that's the disassembler that we've got. I also came across in my research into this that there is an example of the original 6802 Nanocomp. I think this is Mike Spivey, I think it might be. This is his page where he covers the original Nanocomp using the 6802. But the most interesting thing that he had manually disassembled that version of the monitor. And there is a version of it here. So this is ROM M68 in this section here. And this is one of the reasons why you know that the scan code and the key codes and the SVN segment information is at the beginning of the ROM. It also includes many of the subroutines which are identified in the original article, there are addresses given for the various routines like get key and disfresh and these other routines that we've used previously. So what I did was make use of the information that had already been put together in this disassembly. It's not the same code because the 6802 and 6809 are slightly different, but when the 6809 version was produced, there were minimal changes made. There were a few differences in the code, but there weren't a lot of the new 6809 features used, and so the code is pretty similar. I've used this as part of the disassembly. Now, what the 6809 DASM Disassembler has is it allows you to define data files that can include various entries in there, which we'll go into when we show the examples, including saying where is the address originating from, so the first byte, where does that start from? So when we look at the monitor, that's 7C00, and then we can define areas and labels, so areas for data. So this is areas where it will just output the data as bytes, not trying to interpret the opcodes and the post bytes and all that sort of stuff. It just treats it as raw binary data. Labels allow us to replace addresses with a meaningful label. So as we go through the disassembly process, you'll find that it makes things easier if where you have just a binary or a hexadecimal address, that we're able to replace that with a meaningful label. And so, for example, within some of the example programs, for example, you might end up with up to, say, 24 labels for Mastermind, for example. And it just means that rather than looking at a hexadecimal address for a jump, you can say, all right, that's Mastermind 7, what you jump back to. This makes it a little bit easier to understand what the code's doing. And then we can also include comments and comment lines. So comments will go at the end of existing code. A comment line is a standalone line on its own. And what I've done is used the ROM from the Mike Spivey's site to provide some of the comments as a starting point. And what the target here was, there's a particular assembler, ASM 6809, which is a 6809 Windows cross assembler, which comes from 6809.org. So if you just have a look at that, this ASM 6809, this I found works quite well, and it includes a lot of the syntax that the Lance Leventhal book. So a lot of the syntax which is used for the assembler and the macro assembler matches a lot of the books and the sources that I've come across. There are a wide variety of assemblers available, but this was one that particularly seemed to work with the syntax, a lot of the examples I was working with. So again, you could adjust this to work with others. And what I have done is a few minor patches and fixes to the 6809 DASM to work better with this particular assembler. So a few minor changes and things which are needed to make it work nicely. And what we'll be doing at the end of this is, having done the full disassembly, we will then assemble it through the ASM 6809 to produce a new binary. And what we'll then do is to compare that to see whether or not the before and after are identical. Once we know it's identical, then we can know it's a pretty good chance that our source code is generating the same output that the original source did, even though we don't have the source. So it's a bit of a convoluted process. I'd have to say that this takes longer than half an hour, 45 minutes. The process of evolving the data file for the disassembler probably took a number of days over a number of evenings and things. So this is, a reasonable amount of effort to do this. It's certainly not trivial to do, and over time you get a better understanding of how the code works. So I'm not trying to say this will only take you half an hour to do. If you're trying to disassemble something, say a 1 kilobyte program, it is going to take quite a number of hours to do this. But to show you here, you'll be able to see this in hopefully about 20 or 30 minutes or so. So please keep watching, and I'll show you how we're going to do this. We're just going to build the disassembler first. So I've downloaded the zip file already. So we're just going to take the original, this is the original modified zip file. I'm going to copy those over to my working folder here. And then we're going to take the fix files. So these are a few fixes I've made to make it work a little bit better with the assembler that we'll be using. There's also one or two other bug fixes in there as well. And what we're going to do now is just to run Windows Subsystem for Linux using Ubuntu. Just run that up. And we'll just change to the folder so we can access the Windows C drive just through Mount C, and then it's 6809 DASM. We've got the files there, and we just need to do make minus file, make file in uppercase. We have the DASM. Here we go, and we can just check that that's working. And if we do list, it will list every opcode that it knows about. There we go. So DASM appears to be working, and we're going to be running it from here, but we're going to be referencing files that are on my Windows drive. It's probably a bit easier just to drive things from there. So we'll come back to that. What we've got here is we've got the original binary file. So if we look at that in FR head, we can see here it starts at 00 there and goes up to just under 800. So that's a block. 1K is 0 to 400. So this means it's 2K. And what we've actually done here is to split it so that the top 1K is in this file. And we can see here this is only going from 0 up to 3FF. And we can see that we've got our 7089 reset vector there. So this is the file we're going to be working with. We could do it on the full file. It's just that when you're starting this, it's a lot easier to work with just a smaller amount of data and then build it up. So what we need to do is to build up a data file to feed into here. So I've already done this. So I've got a couple of data files here. So what I'm going to do is to copy each data file in one by one. And we'll have a look at that in our text editor. And we'll see that this one is fairly simple. There's not much to this one. So we've got an origin instruction here, and that says that the code starts at 7C00. We've also said that 7089 we know happens to be reset, and there is a comment that goes in there that says the reset handler. We've also put in where the non-maskable interrupt code is as well, and then we've also got the interrupt vectors. So we know from the data sheet what the interrupt vectors are for the various interrupts. So we've got reset, non-maskable, software interrupt, the normal interrupt, fast interrupt, software interrupt 2, and software interrupt 3. So, and then we've then put in data commands for each of those interrupt vectors. So all that means is that the disassembler won't try and decode the values in there. It will just put them out as bytes. So that's a very simple data file. And what I've also done here, I've got the commands because they're a little bit long-winded, particularly because I'm using OneDrive on my PC. The folders do tend to be a little bit long-winded. So we're just going to move that. We've got the files in there. So the command we're going to be doing is just with the origin and the reset vector. And this is going to be output to a text file 01.txt. So let's just see if that runs okay. Okay, so that's run without any rumblings from the disassembler. So if we now have a look at this, not the data one. So you can see that it puts the labels out that we've got defined. But you can see here that starting at 7C00, really we've got illegal opcodes, all sorts of stuff. And the reason is because this is not executable code. When we look back at our subroutines, we'll know that one of the first subroutines starts at 7C00. So this area probably needs to be marked in as data. But if we go to the end, we can see that, oh, we've got our labels here for our vectors. And if we look at 7D89, we should be able to see around 7D89 that, there we go. So 7D89, we've got a load the stack pointer with 13D0. Then it falls down into the non-maskable interrupt where it saves the current stack pointer at a memory location. And then it starts to go into more coding. You can see here that this is where we're going to 7C20 and various other things here. And those are addresses that we know from published in the Wireless World magazine are addresses that we had in our slide here. So if we go back to here, we know that 7C20 is get key. So what we're going to do is to update the data file to have a few more things, and hopefully we'll start to get a bit better information in here. So what I'm going to do now is to copy in our next data file. So this will be the one 02, and copy that into there. And now we'll also take the second command, which is basically we've got the published subroutines, and we've also blocked out some key code stuff. So let's just have a look at the data file first before we go into here. We're looking at the Nanocomp data. So you'll see here we've now got data area for the first sort of 32 bytes. And then we've got the labels for get key and the various other routines that we know about. And there's not much else. So we haven't done much other than what we know, and it's already published. So what we're going to do now is just to run the second command. So this is with the 02. If we now go back and open 02.txt, we'll hopefully find that the beginning of it might make a little more sense. So we can now see that this area here has just been included as bytes, and then we can see get key here, and this is actually starting to make sense. And because this is actually calling, rather than just calling a hexadecimal address, you can see because it knows that disk fresh is in fact a little bit further down here, and it's a relative jump here. So going to disk fresh, and we can go down and see where disk fresh is, and we can see where all these other ones are. And you can see that these ones are in fact calling hex in and various other things. So it's starting to make a bit more sense now. But we will find that there are areas within here where perhaps it will get confused. There might be other data blocks in here. So for example, I know that this code is padded out with zeros between certain blocks. Perhaps in going from the 6802 to the 6809 version, there were changes in the size, and so there are certain bits have been padded out with zeros. Now in this particular case, 0 is not a null byte, it's not a no operation, it's actually negate, I think. So if we see neg around, it probably indicates that we've got another block of data that we need to define. And you'll get the odd warning, error missed a comment line at that particular bit. So you will get warnings from the disassembler as well, but that's looking a bit better. We can now make some sense of that. So let's go on to the next one then. And if we look at our third one, we're refining this all the way along. And remember, this could take quite a number of hours to work your way through this and to make sense of what things are. And if we now have a look at this one, so we've moved a little bit further on. We've probably got a few more comments and things here. And this is where I've started to include the comments from the ROM, the manual disassembly that I think Mike Spivey had done. So I started to put a lot of the comments and things here. So for example, where we're getting the key for the monitor command and things like that. So we should start to see that the code becomes a bit more intelligible. So we've now got more labels and data here. Just going to do this next one. Let's have a look at number 3. Assembly and number 3. There we go. So our list of labels here is getting longer and longer. And as we scroll through, we start to see now that we've got a number of get key labels in here as well. So where there are jumps going around inside the procedures, we've also got the comments that have come from that hand disassembly of the 6802 Monitor ROM. You can see there's a lot more comments and things going in here, starting to make a lot more sense. And there will still be issues, and you can also see down here where we had all those neg codes, we've now replaced that with data, and so they're now just coming out as sort of 0 padding. And you can see here these addresses here are in fact allowing us to intercept the various interrupt vectors here. So this code will actually take an address out of memory. So if we wanted to change the vector, we could change that memory, and then it would mean that rather than, you look at one of these things here, software interrupt 2, for example, 7FD0. 7FD0 at the moment is then taking the value from 13E7. So if we change the address in 13E7, then in fact that will override the software interrupt, and we can put our own code in there. So it's just showing a way how you can allow the monitor to allow certain hard-coded values perhaps to be overridden by values in memory. So that's the next stage on. Let's do the next one after that. So we want to now do number 4. And 4, we're getting very close. We're getting fairly close to having pretty much the Monitor ROM disassembled pretty much. So let us now just do the command 4. So most comments and labels now been done. Let's have a look at this now. That's completed. Let's look at 04.text. Our list of labels and things. You can now see that we've got quite a lot of variables and things have been done now. So as we've gone through, we've identified a lot of the variables and things. So you see, for example, that we're referring to the parallel interface control ports, port A, port B, control port A and control B. There's a lot of temporary values. We've got labels for most of these sort of things now, and there's quite a lot of comments and things. You can see here, this is all to do with the display buffer, is the 7-segment display area. So you can start to see this it can make a lot more sense. We've also got the comments for each of the codes. So when you press M, it calls memdisp, memdisp being the code that runs memory display. So the monitor is pretty much done at this stage, and the final step really was to add the example programs. So if we now look at the 05, rather than being from 7C00, this is from 7800. So this is doing the whole ROM now. Let's just copy this up into here. And we will see here, when we open this, that we've actually changed the origin now to 780. So, and we've now got all of the hexadecimal labels. We've got the calculator, calculate offset, mastermind, and duck shoot. So all those labels have been added. So when we run this now, we should be getting close to getting the entire ROM disassembled. So now we've got our data 5 data file, which has got most of the comments and labels, including all the examples. So now we're using the full binary file, the 1981 binary file, so all 2K of it, and this should get us all of the sample example programs and the monitor. Copy this, paste this in, and that should have run and created it. If we just go to our folder here, look here, we should now be able to look at the output of that. We can now see that we've got hexadecimal, duck shoot, calc offset, and mastermind, in addition to all the other monitor code. You can see we've still got the line numbers and the bytes for the source here. And what we're going to do now is to rerun this. So we're going to rerun this with the same data file, but we're going to include the -C switch here. And what this is going to do is to generate the output in a version which is compatible with the assembler. So once we've got this, we should have close to our final source file that we need to assemble this to create the binary file. So if we now paste this in here, we now should now have the ASM file, With a few tweaks to it, that should assemble into the identical binary. So what we're going to do now is go to our commands and see what the edits that I've worked out that we need to do. So the first thing is remove labels from hex to deck to reset boot. So these are some of the labels we don't actually need to remain in the source code here. So we're just going to go down and remove those down to reset boot. That one. Then the next one is replace equals 0x with EQU $ for the first 13 rows. So these are some labels that we do need to have defined as EQU tags. So we're just going to search for this and we should have that there. So we do replace all there. We've done that one. Macro to search for colon, then down one line to a space, place all labels with colons and move to the next line. Yeah. So what this is doing is just going to remove the colon there and to move the label down to the line with the mnemonic there. So what we need to do this is search first. So that's 120 times. And now we'll probably just run it manually. So let's use the key combination to hit the macro. And as we just get down to the end of the code here in the interrupt vectors. Right, so that's that one. We've done that search and replace. So finally we need to replace the port A direct page with all zeros. What this has come from is that there's a limitation of the disassembler and it's not able to distinguish between 2 0 characters and 4 0 characters. And so what's happened is that this 2 0 port A direct page value has got confused with a 4 0 value here. So we just need to manually correct this. And if we don't do this, what happens is we look at the binary comparison of the original ROM and the new ROM, we'll find there'll be 2 4 0 bytes that are incorrect. So we're just going to do that now. So that's fairly straight. Just need to search for that. So you do this, we're searching for that, and we just need to replace with all zeros. Replace that one. Replace that one. There are only 2 instances of that. Just save that. Now we'd need to review the variables ending in DP for direct page. Again, this is similar to the issue I've just talked about, in that in order for the disassembler to be able to put labels in here, we had to have both a 4-character version of these labels and a 2-character version for the direct page. But when it goes forward to the assembler automatically will adjust the values being used, so we don't need the DP values. So in fact, all we're going to do here is go to home and we're going to search DP. Now, unfortunately, because I chose DP here, there are DP values in some of the arguments to some instructions, like you can see the transfer there. When we get to one where it's an addition to the end of a label, we can just backspace that. So we're just going to go through and backspace where we've got the stray DPs. Part of the reason for this is because this originated on the 6802. There's a lot of use of the direct page register. In fact, with 6809 code, what you would probably do is use a lot of program counter relative offsets, and that produces position independent code and is probably more efficient as well. So it's kind of a legacy, a hangover of the 6802 code that was migrated through to 6809. It uses some 6809 instructions, but certainly didn't change a lot of the addressing. So there's some potential things we could do to the monitor to improve it. We could actually rewrite bits of it to make better use of the 6809 instructions. We're just checking now to make sure we haven't got any stray DPs. So we expect DPs and arguments to all these, but there we go, so that's good. We've done all that. Then the final bit is we have to copy the following. So these are some memory areas which are used for storage, and in order to use the labels for the memory here and to reserve the memory during the build process, we need to make sure we have these labels in here. So if we just put these in after PR, as it says. So again, as part of the understanding of this, as you go through it, you'll identify that, oh, right, we keep on referring to some memory at debuff, for example, which was at 13FA. We keep on referring to it, thereby if we reserve 6 bytes at 13FA here, then the assembler automatically will use debuff where we reference 13FA. So I think that is it. So we've now done all that. All we need to do now is to start up a command prompt, and we've just got to move to the folder where we've got the files. So let's just start this up. Command prompt, and if we just do a directory listing, fine. And if that runs cleanly, then it has worked. So now we need to do is we'll just have a look at the binary files. So if we look at 1981 compared to 2022, and we look at WinMerge, and we'll see, in fact, they are identical, so there are no differences. If we'd forgotten to do that all zeros replacement, we'd have found out that it would be a 40 there and a 40 somewhere down here. So if we do find the difference, then that's normally why. But now we know that we're using exactly the same binary output file, we can be pretty sure that our source code is pretty accurate. And what we can now do is to make changes to the source and make improvements to it. But we know that we can always go back and get back to our original version of the monitor. So I'm just going to have a look here at the output listing file here. So this is the output of the assembler. So we can see up here we've got all our various definitions here, that wherever we see port A, then in fact it's referring to the 4000 address. Port B is 1, control A is 40002. And in fact, when this is used in direct page addressing, the assembler will automatically just use the 02, whereas the disassembler wasn't able to do that. So we had to have a control A direct page of 02 for it to do this. So this is the reason why it's a bit convoluted, but this has taken probably a number of evenings of quite a number of hours. So it's not a trivial process to actually get the ROM to be disassembled like this, but the fact we can now assemble it like this and make changes fairly easily means that we're in a good shape. So we can see here that as it's compiling all this, we can see that there's direct page references here. And when we come down to the main get key, you can see that there's some padding here. So this is where there's just zeros using to pad between the end of the mastermind and the beginning of the ROM. You can see the monitor starts at 7C00, but that in fact the first 32 bytes have in fact got the key code information and the 7-second display information. And what I've done is I've annotated the source. So I've taken the source that we've generated here, and then I've added lots of extra comments and things to make it far more explanatory, and that's the version that we'll be using going forwards. But I just wanted to show how you could use a disassembler to take the image of the ROM and generate the source code from it. It's a little bit tricky to get it coming out all right, but eventually, once you've got all the right steps in place, you can generate the same binary file that you started with, which is a pretty good indication that you've got things right. There are a few other things that the assembler can do. This is not producing a cross-reference of symbols and things like that, but in later videos we can look in more detail at the assembler as we make changes to things. So I hope this is of interest, how to effectively reverse engineer existing binary files that you have either from a ROM or even the program, for example, how to disassemble them, how to then modify them in a way that you can generate the assembly language and then reassemble them and prove that you've got exactly the same binary output file that you started with. So it's kind of closing the full circle. So in number 13, what we'll be looking at doing is adding a serial port to the Nanocomp, and then we'll modify the send and receive parts of the monitor to use the Motorola S19 or SREC format, which is a text file format that the assembler can generate with the binary code necessary to download into the Nanocomp. So by generating SREC format output from the assembler, we'll be able to directly download that into the Nanocomp and then run it. Thanks for watching. If you don't want to miss out on future videos, please hit subscribe, and if you can also hit like if you found this useful, it helps to push the videos up the rankings to allow more people to be able to see it. Thanks for watching.